Today we're diving into a fascinating paradox at the very heart of clean energy. It's the story of something called solar salt. Now this stuff is a hero that helps us capture the sun's power, but it's also got a pretty dark, corrosive secret.
I mean, it's the biggest question for solar, right? The sun goes down every single day. So how in the world do you keep the lights on? Well, the answer isn't just about solar panels. It's all about storage. And that, right there, is where our story really kicks off. So meet our hero, solar salt. In these huge, concentrated solar power plants, thousands of mirrors focus sunlight onto a central point, heating the salt until it becomes a glowing, molten liquid. This liquid can then hold that intense heat for hours and hours, acting like a massive thermal battery that can generate electricity long after the sun has set. It's an absolutely brilliant solution for 24/7 solar power, but there's a catch. To make these plants even more efficient, to make the energy cheaper, engineers have to push the limits. And that is exactly where we run into the salt problem. Here's the deal. Higher temperatures mean more energy, which means lower costs. Simple as that. The goal is to crank these systems way up to around 600 degrees Celsius. But at that temperature, our hero, the molten salt, kind of turns into a villain. It gets super aggressive and literally starts to eat away at the steel tanks that are supposed to contain it. This attack has a name: corrosion. Now, the steel they use in these tanks is tough stuff. It naturally forms this thin protective layer on its surface made of oxides. The best way to think about it is like a suit of armor. The problem is that hot, angry, molten salt is constantly looking for a way to break that armor down. So, that brings us to the investigation. Researchers really wanted to figure out how exactly this armor fails. They started by looking at what happens when the salt is just a tiny bit impure. For their first test, they added just a minuscule amount of an impurity, sodium oxide, to the salt. We're talking 0.005%. I mean, that's next to nothing, right? You'd think it wouldn't make a difference. Well, let's see what happened. So the result here is super interesting and honestly a little weird. If you look at this data, the steel sample actually got heavier. Now, that seems totally backward for something that's being corroded, but it actually makes sense. The steel is reacting with its environment to build up that oxide layer. It's building its armor. It's gaining weight because it's growing this protective scale. So, problem solved, right? Not so fast. The researchers looked a lot closer, and things started to get strange. This quote from the study tells the story. The boundary between the new armor and the original steel, it wasn't a nice, clean line. It was wavy. And that's a huge red flag that the attack isn't happening evenly. Something's going wrong just beneath the surface. And this picture shows it perfectly. This is a microscopic cross-section. You can see that dark corrosion layer on top and the steel below it. That wavy line between them, that's where the salt has started to punch through the armor in certain spots, creating these little weak points. The armor's forming, yeah, but it's already got cracks. This is stage 1 of the failure, non-uniform corrosion. Okay, so that's what a tiny impurity does. What do you think happens when you add just a little bit more? Let's get to the next phase of this investigation, because this is where things get really dramatic.
The researchers upped the impurity level, going from 0.005% all the way to 0.2%. Now, that's still a really small fraction, but in the world of high-temperature chemistry, it's a completely different ballgame.
And look at the graph again. It's a total 180. Instead of gaining weight, the steel sample has lost a ton of mass. This is huge. It means the protective armor isn't just getting cracked anymore. It's being completely destroyed and is literally flaking off into the salt. This catastrophic failure, where the armor just crumbles away, has a name: spallation. And when that happens, it exposes fresh, unprotected steel to the salt, which, just like the quote says, leads to even faster corrosion. It becomes this vicious, destructive cycle.
The evidence under the microscope here is just devastating. Compared to what we saw before, there's no clear boundary, no organized layer of armor. It is completely disintegrated into this porous, chunky mess. The armor has totally failed.
This side-by-side really is the climax of the whole investigation. On the left, you've got the cracked armor, the first sign of trouble. But on the right, with that higher impurity, you see the crumbled armor, a complete and total collapse. It's the difference between a small crack in the wall and the entire fortress falling down. So, after all that detective work, what's the verdict? What do these two very different results actually tell us about how to build better solar plants in the real world?
Well, it really comes down to this clear difference. At super low impurity levels, you get non-uniform corrosion. The armor is there, but it's flawed, it's got weak spots. But once you cross a certain line at those higher impurity levels, the whole game changes. It becomes severe spallation, where the armor is just actively destroyed and flakes away, leading to really fast damage.
And here it is, the smoking gun. The research pinpointed a precise tipping point. Once that sodium oxide impurity in the salt gets above 0.135%, the corrosion goes from manageable to completely unacceptable. That is the line in the sand you just can't cross. So why does a tiny number like that matter so much? Because knowing this is an absolute game changer. It means engineers can set strict purity levels for solar salt. It helps them design tougher, more durable tanks, and they can actually predict how long these super expensive parts are going to last. And most importantly, by understanding and controlling this enemy, we can now safely push those temperatures higher, paving the way for the next generation of hyper-efficient solar power plants.
You know, this whole investigation solves one tiny but absolutely critical piece of a much, much bigger puzzle. It shows us that the future of energy isn't just about big, flashy ideas. It's also about winning these hidden, microscopic battles fought by the materials we depend on. And that kind of leaves you wondering, what other secret battles like this one do we need to win to get there?